we're going to talk about capacitors. Anybody know the symbol for a capacitor? First off, I'd like to do a little diagram type stuff while we talk through how things work.
Squiggly line. It's like a circle with a cross or something?
A circle with a cross? So like this?
Yeah, wow.
It's like that? Is that it?
It's like you read my mind.
Huh. Nope, that's not it.
Half circle with a line coming out.
That's not it.
And then the other side. Like,
so it's like this.
Yep. There you go.
So those are just the connecting lines. So you're going to notice something in this symbol. In the words of Dave Matthews, okay, it's the space between that we need to focus on here. The space between, sorry. These two sides aren't touching. You notice that? There's not like a connector between these two halves. And so when we draw a capacitor in a circuit, let's do like a basic compressor circuit. Common, start, run would be typically how you would do this. And you have your hot coming in this side, which goes to run, and then you would go to your capacitor, and then that would go to start, and then common would go to L2. That'd be the typical way. What you're going to notice here is that start is fed through this capacitor. And if this was a dual cap, this part would be called C, and this part would be called Herm. We connect the Herm side to the start terminal on our compressor. So we're doing some learning here while I'm drawing the diagram. But this part here, this L2 or whatever, I drew L2 both sides. Wow. This L1 on this side here is connected to common on our capacitor. In this case, if it was a single cap, they wouldn't even have a designation. You would just have two terminals. But there's no connection between this side and the other side. So how do the electrons make it through this capacitor to get to the start winding? Does anybody know? Anybody?
There's a little person in there.
Is there? Yeah. He just kind of shuffles them. He kind of pokes an electron over there like, hey. No, the answer is that the electrons do not actually make it from this side to this side. That's not how that works. So it doesn't travel through the capacitor. We may imagine that it does. So in our imagination, when we see a capacitor, what do we think is happening in there? This is just imagination time. There's no judgment here because I think we've all imagined different things. What do you imagine is going on inside that capacitor?
Capacitor's a battery and it's running the compressor.
The capacitor's a battery and it's running the compressor. What else?
And the dual run, the column's applying power to both the fan and the Herm side.
Okay, the dual run's applying power to both the fan and the Herm side, but how?
Through the common, like coming, it makes the connection basically in my head.
Okay, it makes the connection. Okay, what else?
When power comes in and it gets larger and then sends it out on Herm.
The power comes in, it boosts it up, and then it sends it out to the compressor, to the motor, on the Herm side, right? What's actually happening, because we imagine that somehow the capacitor is like boosting, does this sound right? Okay, that it's somehow boosting the voltage or the current or something. It's boosting something.
That's good.
Right? Does that sound right?
Yeah.
It's like something with electricity is getting boosted inside that capacitor. Well, here's the thing. It's actually the opposite. So a capacitor is actually restricting current. It's reducing the amount of current. But it's also creating a phase shift. And it's that phase shift when people say that, that's like magic talk. What does that mean? We're not even going to focus on that too much. But the idea that a lot of people have is that the bigger the capacitor, the greater the phase shift. And that's not true. The bigger the capacitor in microfarads, little baby ferrets. I love ferrets so much, they're so cute. I just love ferrets, and these are little tiny ones. The amount of microfarads dictates the amount of current that can travel into the start winding, or through the start winding, I should say. But our imagination that it's going this way, going through the capacitor and getting boosted up is actually incorrect. The capacitor is like a balloon, or like does anybody know how a pressure tank works for like a well pump, where it actually has a membrane inside the pressure tank? And so as you pressurize, it kind of fills up, and then it maintains the pressure, so that way your pump doesn't have to keep cycling on and off all the time. It kind of has a balloon in it almost. You can kind of imagine a capacitor like that, or imagine that it has a membrane here, and it pressurizes and stores pressure and then releases it. So it's like a balloon storing pressure and then releasing pressure. So as that sine wave, as the voltage changes, because in alternating current we have this constant changing voltage, right? Everybody buy that? If I measure with an oscilloscope or something that's going to actually show the voltage changing on that outlet on the wall, it's not going to always be 120 volts. It's going to be going anywhere from about 150 volts down to 0, and it's just going to keep doing that over and over and over again, right? So when we measure a voltage, we're just kind of measuring an average. It's something we call RMS, root mean square, which is basically a mathematical way of saying what is the average of all these voltages that keep changing. Does anybody know how often the voltage changes? How often it runs through a full cycle? 60 times per second. That's when we say 60 hertz. That's what that is, frequency. How frequently does it go through an entire cycle of up voltage, down voltage, up voltage, down voltage? That makes sense? So in the US, we use 60 hertz. That's 60 cycles. That's a frequency of 60 hertz. A hertz is the term used for that. In Europe, and a lot of other places, they use 50. It's how fast the generator is actually spinning at the power plant. It's literally how fast that's spinning, or how fast it's transferring between poles on the generator, more specifically. All that means is that this little capacitor, this little balloon is inflating and deflating 60 times per second. Can you imagine that? I'm going to wait until that kind of locks into your brain. It's inflating and deflating 60 times per second. And in a balloon, when you're pushing energy into the balloon kind of expands, but then it goes back out the same way it came. Air goes back out the same way it came in, and that's the same thing that happens in a capacitor. So it pushes in, uh-oh, I'm losing my marker. Oh no, oh my gosh. It pushes into the capacitor, and then it pushes back out the same way that it came. So when this connects to Herm, the start terminal on the compressor, it's actually going in and out of the start terminal on the same way that it came in. Now the reason that it stores electricity in the capacitor, this is kind of like strange magic, but it's actually an attractive force between the two plates because we just have so much surface area. So there's a potential difference in voltage across the capacitor, and we have all these metal plates that are wrapped around in a big ball inside or like a roll, a giant roll inside the capacitor. They're all rolled up. It's just a sheet of plastic with metal applied to both sides. And so that surface area, even though they can't touch, creates an attractive force. The electrons store and discharge, store and discharge. So in that sense, it is like a battery. So when we say it's like a battery in the sense that it stores energy. But it's not like a battery in the sense that with a battery, we store energy and then we release it slowly over time. In a capacitor, we're storing it and releasing it 60 times per second, completely. Completely storing, completely releasing 60 times per second. We're doing that, yes, because it creates a phase shift, which helps create kind of that third hand to spin a motor. If you imagine the best way I've always thought of it. Do you guys know what a pinwheel is? Pinwheel? Like you blow it, like it's got the little pin in the center and you blow it and it spins. A little Debbie cake. Are you always thinking about a little Debbie cake?
It could also be like a little cookie.
A little cookie, okay. All right. Is everybody thinking about cookies right now? Why is everybody focusing on cookies? No, but if you imagine something that you're trying to spin, okay, so imagine we've got a wheel, and it's like a Wheel of Fortune wheel, right? What do you do if you want to spin the Wheel of Fortune wheel? What do? Do you just push on the side like, it's not spinning, right? No, what do? We go spin, right? The force of our hand is applied directionally. It's not applied laterally on the sides. And if you imagine 120 volts and 240 as this sort of like side force where they're just directly opposing one another, what the capacitor's kind of doing is it's giving us a third little hand that helps us get it going one direction, and now we apply force on the sides and that kind of keeps it spinning. But in the case of our typical PSC motors that we have, our typical condenser fan motors, blower motors, compressors that we work on day in and day out, single phase, this start winding is actually kind of misnamed because we imagine, because it's called the start winding, that means that it's only in place when the system is starting. But it's actually not. It's in place all the time. The start winding is always having current run through it. Now again, this is where, when I put out these videos, the three-phase guys are like, this has nothing to do with us, and that's true. In three-phase, you've got three hands that are spinning it, and you don't need capacitors. That's why you don't see capacitors on three-phase motors. In single-phase, that's where we use capacitors, specifically single-phase PSC or CSCR. In the case of ECM, like Sam talked about a couple weeks ago, we also don't have capacitors. I mean, we do, but not in the same way. Why don't we see capacitors if you have a ECM blower motor? Because you've all noticed this, right? You have a capacitor on an older blower motor, and on newer X13, as we often call them, or ECM blower motors, we don't have a capacitor. Do you know why that is?
It's kind of built into it.
It's kind of built into it, yeah. But what's built into it?
The module.
The module's built into it. What does the module do? What is that? What happens inside that module?
It's like a balloon.
It's like a balloon? Hey, you're just trying to copy my words. Wrong, false.
There is a little black
It energizes different magnets one at a time.
Now, in that one, I think there's a little man on a hamster wheel.
Man on a hamster wheel, yeah.
He gets out.
He does. That feller and his hamster wheel.
Well, no wonder they fail.
No, so an ECM motor is really a three-phase motor. I'm going to make this really simple. In the same way that you go to a commercial job and that three-phase blower motor, that three-phase condenser fan motor, that three-phase compressor doesn't have a capacitor, that's the same reason why you don't have a capacitor in an ECM. Because that ECM is really a form of three-phase motor. Because what's happening inside that module, really simply, is it's taking power from the utility, 120 volts, 240 volts, whatever, and it's changing it into three-phase. And it's not just changing it into three-phase, it's changing it into three-phase that the frequency can be modulated based on electronic controls. So it's not just 60 hertz anymore on an ECM. It could be 40 hertz, it could be 80 hertz, it could be 20 hertz. The frequency is changed, but it also turns it into three-phase. So now you've got three little hands again. Imagine, again, and this is just the easiest way for me to think of it. If you're trying to spin a Wheel of Fortune wheel, and you've only got two hands, and all you can do is slap on the sides, it's going to be really difficult to get that thing spinning. And that's what 120 volts and 240 volts does. When you've got three hands positioned like this, and you can do this, now you can much more effectively spin a motor. And utility actually always starts out with three-phase. From the power company, there's three phases. But we use a single phase in residential. So we take one of those phases off and we use that to power the entire house. And when we make 240, we take that single phase and we split it into two phases by center tapping a transformer. But either way, whether we're using one in the case of 120 or we're using two in the case of 240, we don't have three hands to work with. And so the capacitor, back to the basics here, our run cap gives us that third hand that helps spin that compressor. But here's the thing, if we have too small of a run capacitor in the system, what does that do to the compressor? Let's say that it's designed for a 30 and we put in a 10. What happens to the compressor?
It doesn't start.
Might not start. Might not start. It's not going to start smoothly at best, right? So what's going to occur inside that motor if you have a capacitor that's too small?
You got a baby trying to spin the Wheel of Fortune?
You got a little baby hand trying to spin the Wheel of Fortune, right? So it's going to get hotter, right? But that heat is not going to be where we imagine. Because we imagine if our run capacitor is too small, that it generates heat in our start winding. That's what we imagine. But that's actually not true. It generates heat in our run winding. So if you've got a compressor, I'm just going to make this really simple. If you've got a compressor that's having a hard time starting, so what does it do? You walk up to a compressor, it's not starting. What's that thing doing? Right? But what's actually happening inside that motor? What's happening?
Baby hands are slapping.
It's getting hot. Baby hands are slapping it, but she ain't spinning, right? Let's see, I like this. Benny's got good metaphors here. He's working with my metaphors. Sam just rolled his eyes. Yes. So that thing's getting hot. But the heat is occurring in the run winding. If you check, and you check start, anybody ever checked start amps or locked rotor amps on a compressor? Put an amp clamp on common and see what those amps are when it's not starting or when it first starts. What are they?
They're high.
They're high, right? They're high when it gets started. It takes a lot more energy to get it started from nothing to moving up to speed, right? And what happens when it stays locked? They stay high until the thing goes out on thermal overload. If we have a capacitor that's undersized, what's actually happening? It's not allowing enough current to move into the start winding. It's not allowing enough to move through the start winding, I should say, because our balloon is too small. If our balloon is too small, then not as much current can move through the start winding because that balloon fills up faster. And this is literally what's happening. In terms of charges, not as many electrons can store in that capacitor when it's a smaller capacitor. That's exactly the same thing that happens when a capacitor is weak. So I have a lot of people say capacitors never go weak. They're either failed or they're either good or bad. Right? Is that true? No. That's bunkum. I don't know why people say that. And maybe it was 20 years ago, back when people used to use the word bunkum. Capacitors do get weak. And when a capacitor gets weak, what does that result in? It results in that motor not starting as quickly as it should, which results in stress on our run winding, because our run winding is staying hotter longer than it should. Does that result in stress on our start winding? The answer is no, because if the start winding has a capacitor that's too low, then the amount of current moving through it is low. And when you have low current, you also have low heat. What happens in our start winding if our run capacitor is failed completely?
Nothing.
What happens in our start winding? Nothing, right? Because without this balloon filling up and discharging 60 times per second, no current whatsoever moves through our start winding. Does our start winding fail when we have a bad capacitor? The answer is no. What does fail when we have a bad capacitor? Our run winding. Why? Because it's sitting there getting powered across the line, and that motor is locked, and it's just heating up until thermal overload takes it out. Thank God for thermal overload, otherwise that run winding would melt the first time the compressor locked. It would just until it just became the thermal overload by melting the winding. When we go to a system that has a failed start winding, often that failed start winding is due to somebody either putting in too big of a capacitor, wiring the capacitor wrong, i.e. across the line, so that way the start winding is getting the full current of the system, or some sort of start gear, like a hard start kit, start relay, start capacitor, something that they wire either wrong or put in something too big or incorrect potential relay size or something like that. So when you go to a system and it's not starting, what are some things you should do first? Let's go through some practical things. Compressor, you go up, drawing high amps. What do you do next?
Visual inspection.
Visual inspection is first, right? And what are you visually inspecting?
Wires, connections.
Wires, connections, that is properly wired. Inspect not just that the capacitor is rated properly, but that it's the correct size for the motor that it's connected to. Is it possible that somebody could have changed a capacitor with the wrong size?
No.
Never. That would never happen, right? Of course it is. Is it possible that they wired it wrong? Of course it is. Is it possible that they put some weird accessory in there and wired that wrong? Of course it is. Is it possible that the wire terminal connected to the contactor is on the wrong spade? Yes. Is it possible that it's melted on the contactor? Yes. Is it possible that it's loose on the capacitor? Yes. Is it possible that it's disconnected from the compressor because it's melted? Yes. Is it possible that it's disconnected from the compressor because the last guy who checked it didn't connect it on properly and then it fell off? Yes, you get the point. So visual inspection is where it starts. All of those things I just mentioned. After you do that and it's still not starting, then I would also check the capacitor, obviously, check the rating, make sure it's the right one, see what that's doing. But then even after all that, let's say it's an older system, compressor's still not starting, what's the next thing you would do?
Check to see if it's in thermal overload.
Well, if it's in thermal overload, it is in thermal overload, because when it tries to start, it shuts off and goes into thermal overload. But if you heard it going, you know it's not, I mean, you know it is in thermal overload because it is locked and overheated, but if it's trying to start, thermal overload is not the problem. Thermal overload is a result of it trying to start and being locked. What do we do next? 8-year-old compressor, 10-year-old compressor, 12-year-old compressor. We've done all of this. We've checked the capacitor. We've visually inspected everything, and it still won't start. What do we do?
Try a hard start.
We try a hard start kit, right? And is that a bad thing to do? Absolutely not. That is the right thing to do. But what does a hard start kit do? A lot of people will say it adds an additional phase shift. Wrong. It does not add an additional phase shift. The phase shift is already occurring in your run capacitor.
Gives you a bigger balloon.
What it does is it gives you a bigger balloon. So it gives you more current to hit that start winding with. But here's the trick. That start winding ain't designed for full current all the time. So now when you put this big old capacitor in there to give it almost unlimited current, what do you have to do with that bigger balloon that you just hooked up?
Turn it off.
You have to turn it off. Bert's answering all the questions now. You have to turn it off, right? Because if that larger amount of current keeps moving through the start winding all the time, the start winding is going to fail because it's not designed for that. It's not designed for constant duty with higher current. Is it designed for constant duty? Yes, obviously, because the run capacitor is connected. But it's designed for constant duty at a lower current. Go ahead, Benny.
Not the same thing as adding, like oversizing the capacitor.
It is, but the difference with oversizing a capacitor is that there's nothing to take it out of the circuit once it gets started. So a start kit gets it started and then brings it out. And that's what a potential relay or a current relay does. It's there so that way once that motor gets up to near full speed, it takes that start cap out of the circuit and now allows it just to run on the run capacitor alone. What is the right hard start kit, the best hard start kit to put on a system?
The one that comes with it.
The one that the factory specifies for it. And there almost always is going to be a specified accessory hard start kit. Sometimes you don't have one using an aftermarket, especially on an older system that you're just trying to get a couple years out of it. That's fine. And that's why I have no issue using hard start kits for that case. Or even in cases where we have some customers in 208 voltage with really long electrical circuits that have high voltage drop. As long as we've established that it's working well, I'm okay with it in some cases, especially in cases where the factory doesn't really specify an accessory hard start kit. But generally speaking, hard start kits we should install factory ones and only as needed, only when the situation requires it. And in some cases like long line sets, the factory will specify it and say that this should have a factory hard start kit in it. But just keep in mind what that's doing is it's just pushing more current or allowing more current to move through the start winding for a very short period of time. It's not some magical voltage boosting device. It's not a magical current boosting device. It's just given a bigger balloon so that way more can move through in and out. Well, all that I'm trying to do in this class, introduce you to some symbols and a few things, but just change your kind of the cartoon in your head of what's going on inside the system because things will make more sense then. If you run into a failed start winding and it's like, yeah, this does have a hard start kit on it, right there. Don't replace that compressor without replacing that hard start kit, and don't do it anyway. Like if you go to a system with a failed compressor on single phase and there's start gear on it, like a hard start kit, that start gear needs to be replaced with factory start gear when we replace that compressor, because it is the most likely cause of electrical failure. If a potential relay locks closed, that'll result in that start winding always taking that higher current. So that big balloon staying in all the time. And that will cause that start winding to fail. What do you replace when you replace a compressor? Factory start gear, which would be hard start kit, capacitor, all that. Make sure, because in many cases, you may get a new replacement compressor that's a superseded compressor that might not actually take the same capacitor as the one that was in there. That happens. So you need to make sure the capacitor is the right size. So let's end with this. What happens in your start winding if your capacitor is too small?
It's not getting enough power back.
It's not getting enough current, right? So it's going to be less likely to start. If it doesn't start, or it takes longer to start, then the run winding takes a hit. It gets hotter than it should, okay? What happens if you put in too large of a run capacitor?
It'll apply too much to the start. Over time, it'll weaken the winding.
Exactly. Over time, it will cause, because you're applying too much current to start, over time, that start winding is more likely to fail. So there's more heat concentrated in the start winding than it's designed for. So is it okay? Just go a little bigger. Is that okay? No. I'll just go a little smaller. Is that okay? No. Why? Because of the reasons we just mentioned. Now, if you've got a 50 and you're going to go up to a 55, you know that the capacitors actually, a lot of cases out of the box, are a little weak and then weaken over time anyway. So would that be acceptable? Use your judgment in those cases, because as a percentage, that's not a significant increase. But this is where a lot of people say, well, yeah, the thing's rated for, a 5, but I'm going to put in a 7.5 because that's all I've got. Well, as a percentage, that's a huge percentage increase. The percentage difference between a 50 and a 55 is a very small percentage increase. Don't use a 7.5 to replace a 5. Don't use a 10 to replace a 7.5. But either way is not good for the compressor. Too weak is not good for the run winding. Too large is not good for the start winding. Make sense? And hard start kits, use them when we got to unlock a compressor. Especially on an older system where we're just trying to keep it running for a while for the customer's benefit. and use it where the manufacturer specifies it. If the manufacturer specifies it, use it, but use the manufacturer specified one. It may take a couple days to get in, but they all are, if they're going to specify it, then they're going to have a specific kit that they specify with the right potential relay and the right start kit or the right start capacitor to accomplish the task. I'll be getting it started, but not overheating it.
So if it's not getting its voltage from L1 because it's not actually connected, where does it get its voltage from?
Oh, you mean the start winding?
Yeah.
It's actually coming through L2. So it's going, pressurizing the balloon, and then it goes back the other way. Pressurizes the balloon, goes back the other way. It's connected to the other side because that's what allows the attracting force, the attracting electromagnetic force that causes the electrons to store and then discharge. If I were to just disconnect this, now there would be no attracting force, and now the balloon doesn't work. So that potential difference is what drives the capacitor, but a capacitor is a super simple thing. It's a run cap it's a metal cylinder. Inside is a jelly roll of plastic sheeting with metal coatings on both sides that are connected to the terminals, and a bunch of oil filled in the inside in order to keep it from overheating. That's all. Crazy simple.
So if it's dispelling the energy 60 times a second for 60 hertz, what causes the capacitor to store the energy? If you were to disconnect power, sometimes they store the energy.
It just depends on where it was in the cycle when it was disconnected.
Okay, so there's no,
like you can, and this is actually a fun thing to do. It's not really fun, but it's fun for me, is that if you take a capacitor, for example, and you hook it up to an outlet, you can literally take one side and hook it to one side of the outlet, the other side, hook it to the other side of the outlet, right? And then disconnect it. Check the voltage on the capacitor. It might be 50 volts. Do it again. Disconnect it. It might be 30 volts. Do it again. Disconnect it. It might be 90 volts. It just depends on the moment that you disconnect it, where was that sine wave in the cycle. The capacitor does not, a lot of people will say, this is another goofy thing, they'll be like, oh man, if you disconnect a capacitor and you throw that up, and that thing stores thousands of volts. It's like, no, it stores whatever voltage it was connected to. When you disconnected it, whatever it happened to be, it doesn't somehow boost up the voltage some crazy way. People get confused because a lot of times capacitors are involved in like inverter-driven systems that have higher voltages intrinsic to that design, but that's not the same thing as a typical oil fill run capacitor that we use, or a electrolytic start capacitor. Those are literally just slaves to whatever the incoming voltage is. That's all they do. They store, they discharge, that's it, their whole lives. Nothing else fancy going on there. You know, for the sake of the video, whenever I do these things, I get tons of pushback. That's not how that works at all. It creates a phase shift, and it's a magical world of make-believe. And it's like, just cut the things open, see what's in them. They're like the world's most simple devices. Don't obfuscate complicated, cover up complicated electrical ideas for things that are very simple for what we do. It's helpful to understand this because when you see a failed run winding, now you know where to look. When you see a failed start winding, now you know where to look. It's helpful when you're discussing with the customer so you don't tell them something crazy that then makes you look dumb later on if they ask further questions, or heaven forbid if they're an electrical engineer. Those people are always fun. All right, thank you all. Have a great week.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.